So the last concept I would like to go over with you in this series are watch variables. Unlike digital, analog, and PWM signals, which have real-world physical representations, watch variables are purely a software concept, but are still essential when it comes to debugging and verifying that your electronic systems work. A watch variable is a name given to any variable within a program that a programmer wants to observe when debugging. Depending on the situation and tools available, watch variables may be viewed when the program runs on its own or step through instruction by instruction. So I thought I would show you an example of what this looks like in Visual Studio, which is an IDE for software development. Don't worry too much about the code or the software in general. What I really want you to focus on is the watch variable window in the bottom left. So I have some mock code here with several variables A, B, and C. And in the bottom left, you can see those variables called out in the watch window. So in this IDE, I can step through each instruction. And you can see that as I step through the instructions, the window in the bottom left show my variable and their current value. And we can see the value changing as I step through my code. My example here is obviously purely software, and the equivalent for hardware applications can be quite different. So now let's move on to how we can implement watch variables for Arduino. Unfortunately, the Arduino IDE doesn't have an integrated tool like Visual Studio to set up watch variables and step through lines of code. So instead, a lot of Arduino users use a workaround by enabling serial communication in their project. This allows programmers to tell the Arduino to send the desired watch variables through the USB cable to then be received and displayed on the serial monitor of their PC. This is fairly easy to do, and we'll go through an example shortly, but it definitely has its limits. This workaround starts to break down when projects require serial communication with other devices, or your system cannot be plugged into a PC. ARCIMUSE can help bypass some of those limits by acting as the watch variable display instead of your computer. The Arduino can send the desired watch variables to ARCIMUSE through an I2C communication channel, which can then be displayed in real time on ARCIMUSE's screen. ARCIMUSE can support up to 10 channels at once, which means that Arduino can send up to 10 different watch variables that can be viewed in real time. For this example, I'm going to demonstrate how to use watch variables for debugging using previous code we developed in the analog signal video. So if you haven't already, I'd suggest you go watch that video first before continuing with this one. In this demo, I will be showing you two methods. The first method sends watch variables through USB to your computer, and the second method sends watch variables to be displayed by ARCIMUSE through an I2C channel. Before that, however, let's first start with what we need to debug. So recall in the analog demo, we used a potentiometer dial to control the brightness of an LED. If you don't have an ARCIMUSE board, your circuit will look something like this. However, this time, I've changed the code slightly such that something is not quite right. No matter what position I have the dial in, the LED stays off. So let's get to debugging our code and figuring out what's wrong. Since this example is so small, it might be tempting just to set all our variables as watch variables and look at them all at once and see which ones don't look right. However, this method will get quickly out of control as you have larger projects with many more variables. So, I want to go through a useful way to break down the problem for targeted and efficient debugging. It may seem a little overkill right now, but it will save you a lot of time in the future if you build the habit right from the start. So recall that first off, our code starts by reading the analog pin and storing it into AIN. Then, using the results of AIN, we convert that to duty cycle, the percentage of the square wave that is a high value. And duty cycle is stored in the DC variable. Lastly, the DC variable is used to write a PWM signal to a digital pin. Looking at this fairly simple flowchart, we can see that there are a few places that things can go wrong. We could possibly be not reading the analog pin correctly, and in that case, AN would be a value we're not expecting. We're expecting AN to be a value between 0 and 1023 and should change based on our potentiometer. Another thing that could not go right is our conversion of AN to DC. For DC, we're expecting a decimal or a float between 0 and 1, and again should change according to how we turn the potentiometer. Lastly, it could be that we're not setting the PWM signal correctly. And so if everything else is correct, we should double check the analog write function to see if we're instantiating it correctly. In order to find the source of the bug, we have a choice of working from the top and making our way down until we come across the correct value, from which we will find where the problem begins. Or we can start from the bottom and work our way up until we come across the wrong value. In certain situations, one will be faster and easier than the other, but is really dependent on the situation. In this case, we'll start from the bottom and work our way up. So I've pulled up a sketch that should be familiar to you from our analog demo. Let's follow our flowchart and check if AN is correct. To do this, we need to start by setting up the serial channel so that the Arduino can transmit the variable value to us. To set it up, inside void setup, we'll type serial.begin, and inside the brackets, we'll type 9600. This opens up the serial port between your computer and Arduino and sets the data rate to 9600 BPS, which is the default speed. Now that that is set up, let's tell the Arduino that we want to send or print the AN variable every time it recalculates it. This can be done with serial.println, and inside the brackets we'll have AN. Now let's compile. And then click Show Serial Monitor at the top of the right corner of the Arduino IDE. So as you can see, it is scrolling down very quickly, but as I turn the dial of the potentiometer, we see values generally move up when I turn the dial up, and generally move down as I turn the dial down. So we can safely say that we are reading the analog pins correctly. So now let's close the serial window and move on to the next part of our flowchart. So now I'm going to just switch AN for the variable DC, but before I hit compile and view the serial monitor again, I'm going to add one more line of code to make the serial output a little more readable. So above serial.println, I'm going to type serial.print, and this just tells us the serial output to not go to the next line. Then in the argument, I'll put double quotations, then type duty cycle. And this tells the compiler that the duty cycle is not a variable name, and I actually want it to print out these letters. This is also known as a string and can be thought of as a string of characters that you type on your keyboard. So don't worry too much about this if it doesn't make any sense. It'll become a little clearer once you see the serial monitor. So now let's click compile. And take a look at the serial output. Now, we see the string that we told the Arduino to print, and on the same line, we see the value for our DC variable. You can't see my ARCIMUSE board right now, but no matter what I do with the potentiometer dial, it stays at 0. So this is not what we're expecting. So I think we have found where our bug is coming from. So let's go back to our code and take a look at where we set our DC variable and see why it's always 0. So we have AN divided by 1023. So the expression here looks like what we want, but what we actually forgot about is typecasting. Recall from our analog demo that since AN is an int and we're also dividing by an int, the Arduino will do its calculation and return a value to the nearest integer rounded down, which will mean that since AN is always a value between 0 and 1023, this expression will always be 0. So let's fix this by casting AN to a float, a decimal number. So now, this tells the Arduino we want to turn AN into a float before dividing by 1023. When Arduino does its calculation, it will also return a float. Let's compile and run again to see if we fix the bug. From the serial monitor, we see that duty cycle now shows a value, so it looks like we've fixed our bug. Now I'd like to go over the second way of implementing watch variables using ARCIMUSE. I'm going to add another bug into our code, and we'll use the same method as before to find the bug. First off, in order to use the functions that enable communication with ARCIMUSE, we'll need to include a library into our sketch. If you think of a function as a book, a library will be where all the information about a set of books is stored, like the name of the book and the words inside it. When the compiler comes to a function, it will go through all of its included libraries to see if it can find the function. If it can, it will read through and follow the instructions set out by that function. We've actually been using libraries this entire time. For example, serial, as in serial.begin or serial print line, is actually a library. However, all the libraries that we've used come with the Arduino IDE, so we've never actually had to declare them explicitly. The ARCIMUSE library does not. So once the library is correctly downloaded, we'll have to tell the compiler that we want to include this library as well. There are two ways to do this. We can go Sketch, Include Library, and select ARCIMUSE, and it automatically places the correct code at the top. Or you can do it manually and just type include arcimuse.h. Next, we need to set up I2C communication to ARCIMUSE. So similar to serial.begin, in void setup, type ARCIMUSE. Now, there's one more thing that we need to do in order to use this library. The topic is a little too advanced to explain right now, but it's pretty easy to follow the syntax and use. We're going to type ARCIMUSE space arc, and this creates an instance of the ARCIMUSE class called arc. An arc can be named anything you like here, and we're going to use this arc in our functions. Now that everything is set up, we want to tell the Arduino which watch variables we want to send to ARCIMUSE, just like with serial.println. This can be done with arc.writeUserChannel, and this takes two parameters. The first parameter is the channel number, so 0 to 9, and the second parameter is the value that we want to send. So since we can send up to 10 variables, let's send 3 different values to the first 3 channels, U0 to U2. So inside the brackets, we'll put 0 and AN. Next will be 1 and DC, but I'll times DC by 100 so we can view it as a percentage on the display. And lastly, we'll put 2 DC times 255, because that's the value we're putting into our analog write function. Let's compile and take a look at ARCIMUSE. So let's scroll through to the user channels of ARCIMUSE. And we have U0, U1, and U3, and it looks like although the channels show some reasonable values, they aren't changing with the dial. So that leads me to believe that we're not reading the correct analog pin. So I'll try turning the dials, and in fact, we see the correct response if I turn the A2 pin. And let's go back to our code and we can confirm that we've set A2 as the AN pin instead of A0. To recap, in this tutorial, we learned what watch variables are, went over a quick example of watch variables in action on a software platform called Visual Studio. I presented a strategy on finding bugs at their source, and demonstrated 2 ways of using watch variables with your Arduino projects. One with using the serial library to show variables on your computer, and the other using the ARCIMUSE library to show variables on the display of your ARCIMUSE board.